So today we're going to cover section 2. We're going to talk about independent and dependent events. So when two events are independent events, if the occurrence of one event does not affect the other. Two events are dependent events if the occurrence of one effect does affect the occurrence of the other. So classic examples of independent events could be spinning a spinner and rolling a dice, or flipping a coin and rolling a dice. The two events have nothing to do with each other. When two events are dependent events, a good example would be like the picture here of this little boy pulling maybe a piece of candy, maybe it's a jelly bean out of a jar, and he takes it out and he eats the jelly bean and doesn't put it back in. That will affect the choice of his second jelly bean. So when something is pulled out and not replaced, that would be an example of a dependent event. So let's look at our first example. It wants us to just determine, are these two events independent or dependent? So a box contains yellow and brown dog treats. You randomly choose one dog treat from the box and you do not replace it. So you're going to feed it to your dog. Then you randomly choose another dog treat. Whenever you do not replace something, when you're trying to choose multiple things from a box or a bag or whatever it may be, then this would be an example of a dependent event. Now, when we go to calculate these probabilities, the results that you do after you take your first choice is going to affect the probability of the second event. So if I did the simply probabilities here, the probability of event A occurring, this is just a review of 12-1, probability of A, I need to count how many dog treats are in my box. I'm going to make up some numbers here. Let's say in the box there are 4 yellow and 6 brown. So the probability of event A occurring would be 4/10, and then simplify to 2/5. Now, without even doing a first draw or a second pick out of the box, just the simple probability of event B occurring, notice there are 6 brown, and that would be 6/10, and it would reduce to 3/5. Now, later on, we're going to do both together, and we're going to see the formula. But just to review 12-1, just doing this simple probabilities here. Let's try another example, just determining if it's independent or dependent. So here it says, a jar contains red and blue marbles. You randomly choose a marble from the jar and then replace it. Then you randomly choose another marble. So because you've put the marble back in, for your second choice, you're still back up to the same number of marbles. So this would be an example of an independent event. So when you're pulling something out of a jar, a bag, or a box, if you just take it out, look at it, and then put it back in, then that is independent. But if you take it out and you keep it, then it would be dependent, because it's going to reduce the number of things, whether it's a jar or a bag or a box. Now let's look at the notation for conditional probability. And this is the notation of how you would write something, that the probability that event B occurs given that A has already occurred is called a conditional probability. And it's written as the probability of B given A, and it's written like this format. Now we're going to see the two formulas for independent and dependent events. So for independent events, A and B, the probability that both events occur is the product of the probabilities of the events. So whenever they are independent and they have nothing to do with each other, you find each simple probability separately and then you multiply them. However, when it's dependent, you're going to set it up as the probability of event A occurring, and then you're going to do the second probability considering that event A happened, and then you're going to reduce the number of total in the thing, and you're going to see what it means by that in a minute.
So it's like a fraction, right?
They're going to be fractions, and then you're going to turn them into decimals and percents. Then the conditional probability, you can rewrite the formula for dependent events to give a rule for finding conditional probabilities. And again, that's going to be the probability of A given that the probability of B is given that A happened. You could divide both sides by the probability of A to come up with this formula. But again, what you're going to be using is this one. Don't worry about this. So here, example 3, you spin the spinner shown. It's divided into 8 equal sections. So I don't need to sit there and count each of the sections. It says, find the probability that you get red on your first spin and blue on your second spin. So let me go ahead and use the letters A and B. I'm going to define my events here. So I'm going to go ahead and state that event A is going to be that I get red on my first spin. So event A, I'm going to define this as getting red on my first spin. And then I'm going to say event B is getting blue on the second spin. So what they're asking me to find is I'm trying to find the probability of A and B. Now, when you're dealing with the spinner, this is an example of an independent event. Because when I spin the spinner, I don't take away that section that the spinner lands on. The spinner stays intact. So when I spin the spinner the second time, it's the same spinner. So these are going to be independent events. So I'm going to be doing the probability of A and B, and that's going to be the probability of A times the probability of event B. So I'm going to do the probability of A times the probability of B. So again, you can see that there are 8 sections. So let me count how many of the sections are red. So I have 1, 2, 3 sections that are red. So my probability of event A occurring is going to be 3 over 8. My probability of event B occurring, I'm going to count how many blue sections I have. And I have 1, 2 blue sections, so 2 over 8, which will reduce to 1/4. I now take those 2 simple probabilities when it's independent, and I multiply them. So I'm going to multiply 3/8 times 1/4. And once I multiply, I get 3 over 32. If it asks you on big ideas to enter it as a fraction, this is your fraction. If it asks for a percent, you can do the proportion or just divide it and then times it by 100. So this as a decimal turns into 0.094. And then if you times it by 100 to make it a percent, 9.4%. And most of the questions on big ideas want you to round to the nearest whole percent. So it would be 9%. So the independent events are super easy. You just find the 2 simple probabilities separately and then multiply. Always reduce all fractions when you enter them into big ideas. Example 4, it says a bowl contains 36 green grapes and 14 purple grapes. You randomly choose a grape and you eat it, and you randomly choose another grape. Find the probability that both events A and B will occur. So eating the grape is like you're not replacing it because you've taken it out of the bowl, you've eaten it, and now there's 1 less grape in the bowl. So whenever we're doing probability, we need to figure out how many total items we have. So the first thing I'm going to do, this is a dependent event because my second grape that I pick out of the bowl is going to depend on the first grape that I picked. So this is dependent. And I need to figure out how many total grapes are in my bowl. So I'm going to add 36 plus 14. I get 50. So now I'm going to do the probability of A. And that's going to be first grape is green. There are 36 green grapes out of 50. I'll reduce that to 18 over 25. Now, for event B occurring, because I've now taken a green grape out, I'm assuming that I got that green grape, not a purple one. So you always assume that event A happened. You got that green grape. So now for event B, given that A happened, I now have only 49 grapes because I took one out and I ate it. And I assume that that grape I pulled was green. So now I only have 35 green grapes. I'm now going to do the probability of A and B. And remember, that is the probability of A times the probability of B given that A occurred. So the probability of A was 18 over 25. I need to go back here and reduce this one as well. 35 over 49, I can divide them both by 7, and this will reduce to 5/7. So that's what I'm going to multiply to my 18 over 25. I can also simplify before I multiply, or you could multiply it as is and then go back and reduce at the end, but I like to do the cross simplification first. I'm going to divide 5 and 25 both by 5, and now I'll multiply what remains, and my probability is 18 over 35. The probability as a fraction is 18 over 35. If I make it into a decimal by dividing 18 by 35, it's 0.514. Multiplied by 100 to turn into a percent, 51.4%. Rounded to the nearest whole percent, 51%. Tell whether the situation is independent or dependent, and then answer the question. So it says, a drawer contains 12 white socks, 8 black socks. You randomly choose one sock, and you do not replace it. Then you randomly choose another sock. What is the probability that both socks chosen are white? So this example here, since we do not replace the sock, this is going to be dependent. Now I'm going to come over here to the side. Now I'm going to identify my two events. Event A is going to be that I get a white sock the first time I choose it. So I'm getting a white sock the first time. Then event B is going to be getting a white sock on the second try. So what I'm going to be doing here is the probability of A and B, but because this is dependent, I'm doing probability of A times the probability of B given that A happened, that I pulled the white sock out. So let's go ahead and do each simple probability. So the probability of event A, I need to figure out how many total socks I have in my drawer. I have 12 plus 8, so I have a total of 20 socks in my drawer, and 12 of them are white out of the 20. I'm going to reduce this by dividing them both by 4, and it'll reduce to 3/5. Then I'm going to do the probability of B given that A happened. And there are now 19 socks in the drawer. And I'm assuming that I got that white sock. So now there's only 11 socks. So now I'm going to take these two probabilities, 3/5 and 11 over 19, and I multiply them. So 3 over 5 times 11 over 19 I can't reduce anything, so I'm just going to multiply. 33 over 95. I'm going to turn it to a decimal. It becomes 0.347, made into a decimal, and then rounded to the nearest whole percent, 35%. So this will be the probability that both socks are white. Now I'm going to do example 2. We have, suppose you flip a coin twice. What is the probability that you get tails on the first flip and tails on the second flip? When I flip a coin, this is an example of an independent event when I flip it twice. I don't take away a head or a tail after the flip. It stays the whole coin. So this is independent. So I'm going to, again, identify my two events. I'm going to say event A is going to be getting tails on my first flip. And event B is going to be getting tails on the second flip. So what I'm trying to find is the probability of A and B, and because they're independent, I'm going to just do the probability of A times the probability of B. So remember, when you flip a coin, you have two outcomes, and only one of them is a tail. So the probability of landing on tails would be 1/2 for the first flip and 1/2 for the second flip. All right, so let's multiply, and I get 1/4. Then as a decimal, 0.25. As a percent, 25%.
Miss Corey?
Okay, so example 6, it says the table shows the number of tropical cyclones that formed during the hurricane seasons from 1988 to 2004. Use the table to estimate the probability that a future tropical cyclone in the northern hemisphere is a hurricane. And then part B, the probability that a hurricane is in the northern hemisphere. So we're going to be doing two parts here. So I'm going to go ahead and add up these columns so I can get the total number of tropical cyclones in the northern hemisphere. And that's going to be 1,142. And then when I add up the southern hemisphere here, this would add up to be 760. So I'm going to go ahead and get my total number. So for part A, I want to know the probability that a future tropical cyclone in the northern hemisphere is a hurricane. So I'm going to be doing the probability of a hurricane given that it's in the northern hemisphere. I'm just going to abbreviate hemisphere. All right, so what I'm going to be doing here is I'm going to set up as number of hurricanes in the northern hemisphere over the total number of cyclones. So let's see. So the total number of cyclones, which I already added, in the northern hemisphere. So the number of hurricanes in the northern hemisphere was 545. Total number of cyclones, tropical depressions, tropical storms, and hurricanes was 1,142. Once I divide this, it becomes 0.477. As a percent, 47.7. Rounded to the nearest whole percent, 48. For part B, they want to know the probability that a hurricane is in the northern hemisphere. So northern hemisphere, and it's a hurricane. So I'm going to go ahead and set it up as the number of hurricanes in the northern hemisphere. Same thing as before. back here when I did this calculation, up here at the top, this 760 was for the total number of hurricanes. So that's what I'm putting here, the total number of hurricanes. So I want to know how many hurricanes out of the total are in the northern. So 545 over the total number of hurricanes, 545 plus 215 is 760. And then as a decimal, 0.717. As a percent, 71.7. Rounded to the nearest whole percent, 72. Last example says you randomly select 2 cards from a standard deck of 52 cards. What is the probability that the first card is not a heart and the second card is a heart? First, if you replace it, and then second, if you don't replace it. So we're going to do it 2 different ways. So again, remember there are 13 clubs. There are 13 diamonds. And there are 13 spades. And then there are 13 hearts in a standard deck of cards. So let's go ahead and let's identify our events. I'm going to say event A is going to be that my first card is not a heart. And then event B is going to be second card is a heart. So for part A, I'm going to be doing probability. For both part A and B, I'm doing probability of A and B. But remember, we are replacing it for part A. So this would be independent for part A because we're replacing it. So what we're going to do here is just going to be the probability of A times the probability of B. So remember, there are 52 cards in the deck. So if I do 52 minus 13, that's going to give me how many cards are not hearts. Because we have 13 plus 13 plus 13, that's 39. Diamonds, clubs, spades. So the probability of not a heart is going to be 39 over 52. The probability of the card being a heart is going to be 13 over 52. Now I'm going to reduce these fractions. This one, the probability of A, both by 13, and reduce this to 3/4. 13 over 52 is going to simplify to 1/4. You definitely don't want to try to multiply these 2 fractions as is without simplifying them. Otherwise, you're going to have a huge number that you're going to have to go back and reduce. So then we would get 3 over 16. And then if I make this into a decimal, it's 0.188 as a percent, 18.8. Rounded to the nearest whole percent, 19%. Now, if I do not replace it, then for part B, still probability of A and B. So I'm doing the probability of A, and then for the probability of B, given that A happened. And again, I'm assuming that when I pulled that card out, that I was that I actually got not a heart. So here what I'm going to do, the probability of A is still the same. It's the 39 over 52, which again reduces to the 3/4. However, for the next one, probability of pulling the heart out, I have now 51 cards to choose from because event A happened. I got the card that was not a heart. So this one still has 13 hearts left. So now I can multiply this, 13 over 51. I can simplify before I multiply, make this a 1. 3 goes into 51 17 times. Multiply what remains, and I get 13 over 68. Divided and made into a decimal, 0.191. As a percent, 19.1%. Rounded to the nearest whole percent, 19%. So notice both percents rounded are the same thing, whether you replaced it or not. But more exact, the first choice was a little bit less. It was 18.8, but the other one rounded, they both round to 19. And that is it for the notes on 12.2.